Welcome back to the fourth and last lecture of the first part of our mini-course Medical AI, from decision support systems to causability. So this is the overview. We are now here at part 4 and we will deal about causal reasoning and interpretable AI. Let's look at our agenda. So at first, as usual, we do some reflection, a follow-up from last lecture. Then we will spend a little bit of time on the history of decision support systems, because this is at the same time a history of AI. Then we will see how causality and decision making fits together. A little bit digression on medical communication, and that brings us directly to causal reasoning, and we finalize with interpretability. So let's start with the reflection. So what do you see in this picture? What is this? Yes, this is the famous receiver operating curve or characteristic. So it is the measure, so the area under the curve is a direct measure for the performance of algorithms. Here in this case, you see there is a comparison between, for example, artificial neural network. So here this is the full line, and the dotted line is the support vector machine, so that you can quantitatively judge how good the performance of these algorithms are. So this is a benchmark for measuring the performance. Next picture, what do you see here? Yes, this is the model of Wickens, so how we make decisions. It is still currently the best model we have, so it is a simplified model. The good thing is that it kills two birds with one stone. Do not worry, we do not kill any birds, but this model fits beautifully together with Bayesian Laplacian theory of learning, and at the same time it is built on the Atkinson and Shiffrin 3 level or 3 memory system. So this is really very good, a very good image. Yeah, what do you see here? Yes, again, the receiver operating curve as a signal noise detection. So this describes when we say yes or no in a certain decision. And finally, what do you see here? Yes, this was maybe one of the first or the oldest is decision trees, and decision trees go back to ancient Greece, and decision trees are still used and are state-of-the-art in modern medical AI. So this is really a very good model. Okay, then let us discuss a little bit the history of AI. So what was the cradle of early AI? So really it starts with 1943 McCulloch-Pitts, where they tried to, from these biological neural networks, they tried to implement an electronic or a mathematical model of a human, let's say, nervous cell. So they called it artificial neuron, and this was the cradle of all of the resulting and ongoing machine learning models. So in 1950, the famous paper, Computing Machinery and Intelligence, Can Machine Think? Then 1958, an implementation of John McCarthy, the advice taker, Programs with Common Sense. And then in 1959, a study on using the game of checkers. So the first artificial intelligence was concentrating on games. The game of checker, for example, later on the game of chess, and most recently the game of Go. Yeah, and in 1975, we have high time in artificial intelligence. So this is the famous model of inexact reasoning, the Mycin model, developed by Shortleaf and Buchanan, and this was really the high time of artificial intelligence, of classical artificial intelligence. And in 1978, again from Richard Bellman, Can Computer Think? and then the progress decreased in artificial intelligence, and we developed the winter of AI, but a little bit later about that. So slightly the 5 decades of health informatics. 1957 was a cornerstone because of the Sputnik shock of the Americans. And from there on, it was many successes were going out of this, and medical informatics as well. And this was tightly connected with artificial intelligence. So, although the focus was on data acquisition, storage, pure computing. So this is the early time of expert systems. Yeah, and the term was first used actually in 1968, and the first course was set up 10 years later. So in 1985, we know during the AI winter, mobile communication became very interesting, and health telematics was evolving. So healthcare networks, telemedicine, CPO systems. So CPO is short for computerized physician order entry. So this was on vogue at this time. This is just a process of electronic entry of medical practitioners' instruction for the treatment of patients. So these orders are then communicated over a computer network, and this is then distributed to the medical staff or to different departments, so responsible then for fulfilling the order. Yeah, and 1995, web era, here artificial is forgotten, and during this time or even later on, it was not very useful if you even mentioned the name artificial intelligence. So AI was here completely forgotten. The web was in, the semantic web was ongoing. So web-based application services, electronic patient records appeared, distributed systems. So there was a lot based on the internet and particularly on the web. So in 2005, then we have this, let's say, this rebirth, the AI renaissance, with the huge success in statistical learning due to the availability of data and due to the availability of computational, let's say, power. So pervasive computing, ubiquitous computing, Internet of Things, this was on high tide at these days. And 2010 then, big data is here. This is super for AI. This means a massive increase of data. So the challenge now is more focused on data integration, data mapping, and so on. And now we are in kind of an explainable AI era where the goal is to make sense out of the data, to disentangle the underlying concepts toward causality and causability, which we learn in this part, in this lecture of our mini course. Okay, so what is the prototypical expert system or decision support system? So you see Dendral was at the very beginning, so this is the top root in this slide. And this was originally, this Dendral system was originally a procedure, a computer procedure for non-redundantly enumerating topologically distinct arrangement of a given set of atoms. So atoms in the sense of information atoms, consistent with the rules of chemical valence. And conventional system had failed to support these organic chemistries in this forecasting of molecular structures. So human chemists knew that the possible structure of any chemical compound depends on a high number of rules about how different now atoms, physical atoms, can be bound to one another. And many facts about different atoms are in such known compounds. And this was then the first system which really was outgoing for the further development. And Mycin was the next system. So Mycin is the first really available prototype of an expert systems. We will develop some time or spend some time on discussing Mycin later on. Okay, so what is the architecture of such a typical decision support systems? Dendra was well known to computational chemists. They had a lot of work to do with it, and although it does not exist up to date, it had a major impact on the field of artificial intelligence and the evolvement of what is known as knowledge engineering, which is both the science and engineering of this knowledge-based system. So actually the classic artificial intelligence was rather called knowledge-based systems. And this applies from a lot of methods, different methods, from data mining, from decision support, from mathematical logic, and particularly from cognitive science. So a great amount of work was spent in observing how human experts work, and they spent a lot of time to design models with their expertise. So, and Dendra was a spin-off from this, so the Mycin was a spin-off of this Dendra, and this was also very, let's say, basic, a fundamental for classic AI research. And here you see the structure. So if we look at this picture, you see here the core. The core is the inference engine. Here is the knowledge base. And this is administered by a knowledge engineer. This is a mathematical computer scientist. So this is a logic engineer, and here the domain expert. This is then the medical expert or the biological expert, the biomedical expert. And though they both, let's say, do the rules, develop the rules for the knowledge base, and the inference engine works then via a user interface with the user. And actually, this is really a good example for explainable AI at this time, because you could, for example, get advice and you could retrieve explanations, so direct explanations. So these systems were very transparent. And the disadvantage was that it was only working on a very narrow field. So this was the big disadvantage. So what is then static knowledge and dynamic knowledge? So here you see the database with the general factual knowledge of the domain, here the biomedical domain. And then you have these production rules. This is called static knowledge in this system. And then you have dynamic knowledge. That means constantly in interaction with the user. You have facts about the problem entered by the user. You deduce, which this is retrieved from the system by the rule interpreter and so on. So you have really here an explanation capability, and this was constantly in interaction with the user. So this is really a good example for early explainable AI, and this was in 1975 onwards. So this really was a cornerstone in this field. So how to deal with uncertainty in the real world? This is the basic questions. So we are now already well aware about the notion of probable information, if you can remember our previous lectures. So the classical problem now is that the information available to us or to medical experts, to you, is often imperfect, imprecise, uncertain. And this is especially in the medical domain the case. So a human agent can cope with deficiency. You can deal with missing information. So you do not necessarily need exact information. So, and as you know, and as I have mentioned several times, in the medical domain, we have mostly to do with inexact, incomplete, uncertain, noisy, dirty, unmeasurable, and so on. So this is a big problem basically in the biomedical area. And classical logic, this classical AI, permits only exact reasoning. And this is really very, very problematic. If A is true, then A is non-false. And if B is false, then B is non-true. So this is really now a problem in dealing with uncertainties of the real world. So, and you know, most real-world problems do not provide this exact information. So mostly it's inexact, incomplete, and even unmeasurable. So what are the certainty factors? Then let's now do a closer look at this Mycin system. So Edward Shortleaf was aware of these problems involved with classic logic, and he introduced therefore a certainty factor. So let's say, what is Mycin? Mycin is a rule-based expert system developed by Shortleaf, which is used for therapy planning for patients with bacterial infections. So we concentrate on the domain of bacterial infections only. So this is one of the disadvantages of the system, that it only can deal with these bacterial infections. So it is based on goal-oriented strategy. This is called in German Rückwärtsverkettung. So that means to every rule and every entry a certainty factor is assigned, which is then between 0 and 1. And you can remember, I have often mentioned this marginalization, this dividing by the evidence. This is exactly something that you have a quantifiable measure which is easy for you. So, and this works with Mycin, so because two measures are derived, so you have a measure of belief and you have a measure of disbelief. And then you can easily calculate the so-called certainty factor CF of an element by CF of hypothesis H equals to measure of belief of the hypothesis H minus the measure of disbelief of the hypothesis H. And if the certainty factor is positive, then more evidence is given for the hypothesis, otherwise the certainty factor is negative. So if you have an hypothesis, for example, that this patient has COVID-19 and the certainty factor is 1, then it is sure. If it is minus 1, then it is completely false. And now, if it is 0, then you cannot say anything because you don't know it. And this is the big advantage. So you have an hypothesis which is 100% true only if you have plus 1, and an hypothesis is minus 1 only if it is 100% false. And now you have a good middle way. When you have received 0, then you know you cannot rely on this machine. So this is very good. So now let us look at an original example. This is was published in much later on. So this was originally working from the 1960s onward to 1975 and so on. And this was published in 1984. So hypothesis 1 is the identity of organism 1 is Streptococcus. Hypothesis 2, patient 1 is febrile. Hypothesis 3, the name of patient 1 is John Jones. And now we get results based on the data inputted into the machine. We get results. So for example, certainty factor that hypothesis 1 is true with an evidence of 0.8. So there is strongly suggestive evidence that the identity of organism 1 is Streptococcus. So this is quite a high value. So you can be quite sure that it is Streptococcus. Okay. And certainty factor of hypothesis 2, given the evidence, is minus 0.3. So there's weakly suggestive evidence that patient is not febrile. And then certainty factor hypothesis 3, that is plus 1. It is definite that the name of patient 1 is John Jones. And you see, so you can check your hypothesis and then you can combine this with logical operators. So why was Mycin no success in clinical routine? And if you have time, then please look up this nice movie at YouTube. This is called Real Triage Nurse, and this is a funny statement, but has a serious background why this was not a success in clinical practice. However, we have to acknowledge that this was pioneer work for practically each following system, and practically it really contributed to artificial intelligence at this time. And as I have mentioned before, these are beautiful examples of what is now called explainable AI. But the huge limitation, of course, that these systems were not able to deal with uncertainties of the real world. They needed complete data, and most of all, they were only focused on a very narrow domain. Okay, so why was AI so on vogue in the 1970s? Here, a nice magazine from this is from 1968. So this is from May 1968. So die Geheimnisse des Rechenautomaten. So even in a Vogue in a Mode magazine, there was discussed the possibilities of this upcoming artificial intelligence. And please remember, and this comes out here beautifully, we are dealing with 0 and 1. So they are well aware that we are talking about computational machines, so Rechenautomaten. Yeah? And therefore, I'm showing this to you that you always recognize that this is working on computational machines. Yeah, and cybernetics was the name of this at this time. So it was praised for the solution of everything. So here, image from 1970, where you have cooking as a cybernetic principle. Unfortunately, the AI winter was then bitter cold, so we rapidly lost interest due to the unsuccessful approaches, and then we were faced with a deep bitter cold winter. And here's a nice picture. So here the attendance of persons, of people, of scientists at scientific conferences. So here you see 1982, 1985, a peak here up to 5,000 and more, and then it goes down, goes down, and goes down. So at the moment, here you can see this renaissance again. So if you have a look at this, so while here in the 1980s you have this peak, now we have this bitter cold winter. Nobody was interested in artificial intelligence. So you see, up to 2010 this was the case, and now recently, very rapidly, it nearly explodes. The interest explodes and goes back, and everybody is now talking about artificial intelligence and machine learning. Okay, so this is a really nice slide by Andrew Beam from the Department of Biomedical Informatics of the Harvard Medical School. So please have a look at this slide. So this is really very nice. It shows you in one single slide the history of artificial intelligence, and this is closely connected with medical informatics. So here you see, starting from 1940, you have McCulloch-Pitts. Then in 1950, Frank Rosenblatt, for example, the perceptron. This is really the forerunner of the neural networks. Then you have Marvin Minsky and Seymour Papert, the famous cognitive scientists, with the XOR problem here. Then the dark age, the AI winter begins. Then perceptron was defined or redesigned as multi-layered perceptron, and with back propagation. This was then the success for that, what is now our success example, what you have seen in the lecture number 1, and then ongoing success with this deep neural network, and this is now up to date. Okay, so what is the problem with the current state of the art? Current data-driven machine learning approach of artificial intelligence misses an essential element of human intelligence. And now you can guess what this is. Of course, AI cannot reason why. So the question of why, I have mentioned this several times. So we can really understand even complex problems, and sometimes we are able to explain and find out the reasons why, but the machine cannot do so. So AI cannot reason why. So and this brings us now directly to causality, and this is really tightly connected with decision making. So causation, beware of counterfactuals. David Hume, causation is a matter of perception. Observing fire, for example, result feeling heat. So this is the classic example with the Kind and the Herdplatte. So you touch the fire and the result is feeling heat. And Karl Persson was against all this. He said, forget causation, you should be able to calculate correlation. And he stimulated the big hype in statistics, in the classical statistics. And they banned the Bayesian ideas, they banned these causation problems. They just purely focused on calculating correlations and said, if you are able to find correlations, this is the big thing. Yeah, and Judea Pearl then, he said, be careful with purely empirical observation, instead define causality based on known causal relationships and beware of counterfactuals. And we'll get to know this in the next slide. So, for example, what is a counterfactual? Here you see a causal graph for a randomized experiment. So we can estimate certain counterfactuals by reweighting data collected in the past. This is asking the famous what if question. So what would have happened if you changed, for example, treatment U in your intervention? So this is a classic example, and Hume said again, if the first object had not been, the second never had existed. So this is the causal chain, and causal inference can be seen therefore as a missing data problem. So you see here beautifully comes together the thinking of classic philosophy with the thinking of machine learning and current artificial intelligence. So remember, correlation is not causality. So back to our AI, it is always important to remember correlation is not causality. Here a really famous paper by Robert Matthews from 2000, and he beautifully demonstrated that the hypothesis storks deliver babies is completely true, simply correlating the birth rate with the number of storks in the country. And this is a beautiful example what you can do with pure causality, with pure correlation and ignoring the question of why. Why is this the cause? Why do storks deliver babies? So correlation does not tell anything about causality. This is very important to note. And one of the few people who understood this very early was Reichenbach, Hans Reichenbach. He post-hume in 1956, he published his common cause principle, and this common cause principle links causality with probability. So this states that if x and y, you can look it here, if x and y are statistically dependent, there must be a set influencing both. So here, for example, you have the storks and the babies, and both are influenced obviously from a set which is an unknown. And now you can ask the question, what is this unknown? And maybe this is let's say industrial development factors and so on. So here this is the unknown influencer set. And the big question is to find this set, and therefore to find out then how to get x and y independent. Okay? So what is a functional causal model? So a functional causal model can help here to satisfy this before mentioned Reichenbach principle. So let us assume, if you look here, we have a set of observables, so x index I until x index n, and this is our set of observables, and then we can arrange them in a graph. You can see this here. And each observable is determined by its parents here. So this is mathematical parents, not physical parents. And look at the yellow node now in the middle. This is x, y as a function of the parents of x, y, called PA as a function of j of PA, BAG. Okay? And we call then, and here you have a second part here. This is the interesting unobserved unknown, therefore unknown j, uj. And we call this noise because this is unknown. And now it is a very hard task, as you can imagine, because it leads us to the question, can we infer the unknown, this unknown here, can we infer this unknown from purely observational data? So I stop here because this is only partly solved, just that you have a feeling what the counterfactual is. But here I would really recommend to read on with further literature. Okay, a few words about counterfactual learning, because this is important for us in the machine learning domain and machine learning for health, so medical AI. So the first step in the ladder here, this is the ladder by Judea Berl. And the first step is association. So the activity which we are involved is seeing, or technically speaking, observing. And the question is, what if I see? How are the variables related? How would seeing X change my belief in Y? And typical examples are, what does a symptom tell me about a disease? What does a survey tell us about, for example, election results? And there's a second step, this is the intervention. So here we have the activity doing or intervening. The questions now, what if I do and how? So what would Y be if I do X? And how can I make Y happen? So example, if I take aspirin, will my headache be cured? What if we ban cigarettes, for example? So typical questions. And the third step is then, according to Judea Berl, the counterfactuals. So the activity here is imagining, retrospection, and understanding, exactly what we want to achieve in the field of explainable AI and interpretable machine learning. So the question here would be, what if I had done and why? What is X that caused Y? What if X had not occurred? What if I had acted differently, for example? So, for example, was it the aspirin that stopped my headache? Would Kennedy be alive if Oswald had not killed him? What if I had not smoked for the last 2 years? So you see, these are the typical counterfactual questions. And here really I recommend to study the Book of Why. This is by Judea Berl, The New Science of Cause and Effect. And this is really a fundamental reading for understanding this medical AI stuff. Okay, here you see now what each layer. So back to the examples. So this is now taken from lecture 1. If you can remember our very successful machine learning example, they used a neural network, a certain neural network. This is called Inception V3. And now we look, what do the layers learn? So we look inside the network. So here you see what each layer learns. Starting, if we look here, we learn first primitive edges, for example, then more complex shapes, and then shapes up to higher level features until the classification result. And now it is a good time to mention what explainable AI actually is doing. And we will see this on the next slide. So what can explainable AI methods do? So you have learned, and if you can remember from the past lectures, that all these machine learning methods have the big disadvantage that they are hard and difficult to understand. So how can we make them more understandable or retraceable? Okay. How can we make it transparent? Let us look at this example. So here we have the image, and you know there's no talk without a cat, showing a cat. So this is the machine learning cat here. So this image is converted to feature vector representations. You have heard this several times already. And then we can classify this into a cat or no cat. And now the classifier is applied to assign the image on a given category, and then the method, for example, this particular method, this relevance method, this can then show you how the or what contributed to make a cat a cat. You see it here. So red is most relevant and blue is most irrelevant. So you see a certain aspect of making a cat is this whiskers, for example. Yeah, and this is called the layer-wise relevance propagation. Why layer-wise? Because each layer is checked like that, and the final relevance is visualized. So you see the contributions of each single layer and each single pixel to the prediction then at the end. So first the input image is processed by the network, and then you look from the network back. So the output value is back projected layer to layer, resulting into pixel relevance values, and this can be visualized by a heat map. So this is the heat map here, and this is how it works, layer for layer. This is forward propagation, and this is then layer-wise relevance back propagation. And then you get the relevance score out of it, and then you know which pixel or which layer, which pixel do contribute to make a cat a cat. So this is just an example how this explainable AI method works and what it can do for you. So why is explainable AI only a first step? So if we look at this slide, so you see that of course we would like to use glass box methods where we can look into the method. So here you have the input data, then you have the machine learning algorithm. Here the styled theta parameter, the Greek parameter theta for the feature, and then the human is observing the result. And of course, we would like to use glassbox method, but as a matter of fact, currently the best performing methods in medical AI are of black box nature. And although, for example, people like Cynthia Rudin are asking for stop doing explainable AI, if we want to use these successful methods, then we have to do it. I could also simply say stop drive petrol-driven vehicles worldwide. Yeah, so it is possible, but unlikely. So here you see then a possible solution. So you see why we need this explainable model. So you have here this we have this black box model, and that means we need an explainable model as we have seen before. So this would be the layer-wise relevance propagation here, but still open is the violet aspect here. So how, and this is an open question, how should future human AI interfaces look like? So this must be surely explanation interfaces. So we need human AI interfaces which allow exactly to ask questions as we have learned before, such as the question of what if question, and this allow to ask our explainable model. Okay, and then you have an idea that you can make still transparent the black box model. Okay, but now let's go back to the more hospital-related topics where you are more interested in. So this is medical communication. So you see what are the key problems in medical data management? So you have the classical patient data, you have clinical data, you have laboratory data, many data, different features contribute to one result. And please remember, the key problems in dealing with this data include the heterogeneity of the data source that needs the data fusion, data integration aspects, the complexity of the data. All this data is of very high dimensionality. We have always this problem with this noisy, uncertain data, dirty data, missing data, wrong data, and so on. So there's the challenge of pre-processing. And then, of course, we have this discrepancy between data, information, knowledge, as you can remember these various definitions. And then, of course, this is really big data, and this makes manual handling of the data nearly impossible. So we need computers for that. So what is the combining link? Again, I have shown this picture before. So the combining link is text. And why is this the case? So there is a famous question, is a picture worth 1,000 words? And the logical answer is, it depends. So some researchers are arguing that sometimes a picture might be worth 1 billion words, for example, whereas others are arguing that sometimes text is much better than an image. So it completely depends on the context and depends on the use, where you use it. And so the medical record so this brings us now to the medical record, because this is legally binding. So the written text is legally binding. So, and be aware that most information in hospital is available in this text format, and text is the communication media in patient findings, and the amount of this data is immensely increasing, and consequently text and handling text is a huge area of machine learning and medical AI. Okay, so the teamwork in the hospital requires a lot of communication and information exchange, text exchange at the end of the day. So the vision of such a business enterprise hospital information systems is to cover all these workflows, organizational processes, and information flows electronically. And the quality of the work of physicians, so several studies proved this, is heavily influenced, of course, by the usability and the available equipment. So, and here in this slide, you see a typical work meeting of medical professionals where they discuss the patient cases jointly together. So many different people contribute to one single result. And if it is important to study and understand the workflows of the end users and to involve them into the development of such systems. And this will be done in part 2 later on, part 2 of our course, when we do more practical things, like, for example, asking for how can we bring AI into the direct workflow of our medical processes. But this is later on. So let's go back to the problems of this text. So the aforementioned goal produces really a lot of this text, and this is really, the handling with this text is not easy. And why is it not easy? Because of the special words, so of the language mix, for example, yeah, and the many abbreviations, and logically there are a lot of errors inside. And this is not a joke. This is really a real world example. And medical German is a worst case. This is a mixture between Latin and local abbreviations. This is even hard to read for humans, but humans can. So this is not a joke. So humans can make sense out of this, but for machine, this is really a difficult task. So there is no AI who could read and make sense out of such text. Okay. So for example, just that you have an idea, this one clearly states the Antrum-Schleimhaut ist durch Lymphozyten infiltriert. So you can clearly read this. But the problem now is a ongoing problem, because now you have the Antrum-Schleimhaut ist durch Lymphozyten infiltriert, but this can also be lymphocytäre infiltration der Antrum-Mucosa, and it can also be Lymphozyten-Infiltration der Magenschleimhaut im Antrum-Bereich. It's one of the same. So now how should the AI, even the best AI, know in which context this should be read? So this is really a difficult task, and shows you the problem that it's not so easy to solve this. So why does language understanding require knowledge at all? So you need the syntax. So syntax, this is the set of rules and principles and processes that govern the structure of the sentence in any given language. So disregarding whether it is German or English or whatever, specifically word order. Then you have the semantics. So semantic comes from ancient Greek. Semantikos means significant. So this is primarily the linguistic and philosophical study of the meaning, Bedeutung. So in a programming language, you have this formal logic logics and the semiotics. So it focuses on the relationship between so-called signifiers. So these are like words, phrases, signs and symbols and what they stand for and their donation. And then pragmatics, a total different subfield of linguistic and semiotics that studies the way in which context contributes to meaning, Bedeutung. Yeah? And pragmatics encompasses, for example, speech act theory, conversational implicature, and talking interaction and other approaches to language behavior. And this is mostly used in linguistics. So, and unlike semantics, then you have the context. So the context is maybe the most difficult one. Therefore, I have highlighted it here. So, and we are far from be able to understand the context with machines, pure machines. So therefore, and this is a further very, very good aspect of why we need the human in the loop, because sometimes, not always, sometimes the human can understand the context. So, and then of course we have this emotion which is not tackled by AI at the moment, but is genuinely human. So this is also a very interesting part. Yeah, and here a classical example from Stanford. So this was misclassified from a video surveillance camera, and this caused an police emergency Einsatz, and the police came and thought there's a young boy holding a baseball bat. Instead of this is a baby holding a toothbrush. So you see, these are these typical contextual misunderstandings. Okay, so this is just for you to round up. So text is a good example for non-standardized data, because many factors contribute to the meaning of this linguistic data, and we will skip this and go to causal reasoning. So how can humans understand the context? So how do humans generalize? From few examples, we have mentioned this already. They learn relevant representations, so are more precise. They are able to learn these relevant representations. They can, for example, answer the question, what is relevant? And what is relevant is a really pressing question. They can disentangle these explanatory factors, these underlying explanatory factors, which needs insight into this, and they can find these shared underlying explanatory factors, in particular of P of X and P of Y given X, with the causal link between Y and X. So this I have shown before, and you now see how humans can do that. And how can we deal with it in artificial intelligence? We need causal relationships with these diagrams. So this is, for example, these graphical models. So for example, in the case 1 here, X causes Y, and in case 2, X so Y causes X, but there could be a hidden confounder Z. This explained an unobserved dependence, okay? So, but case 3 here, X and Y are completely independent. And in case 4, there is a complete dependence. It is a feedback relationship here. And in case 5, we have a hidden confounder which explains the relationship. Think back to the shown baby, the storks deliver baby example. So this is a typical example like that. And the last case 6 is conditioning on a hidden variable S, which explains an observed dependence. So this is just that you see how you can work with this in knowledge engineering, in knowledge extraction. So actually this is a good example for knowledge extraction, which you can use then for machine learning, artificial intelligence. So what is then reasoning? We have often now talked about reasoning. What is reasoning or sense making? So in German, Schlussfolgern, Argumentation, Beweisführung. In informatics, we say inference, and sense making can be translated in German as sinnmachend. Yeah? So, and what is this? How can we do that? So we have deductive reasoning, for example. So we have an hypothesis, we have observation, observations and we draw logical conclusions. Here's a danger. The hypothesis must be correct because the deductive reasoning defines whether the truth of a conclusion can be determined for that rule. So based on the truth of premises, A equals B, B equals C, therefore A equals C. And you know all these examples of this deductive reasoning. So inductive reasoning is then making broad generalizations from specific observations. Here also a danger. This allows a conclusion to be false if the premises are true. So you generate hypotheses and use then deductive reasoning for answering specific questions. And the third case is abductive reasoning. This is inference to get the best explanation for an incomplete set of preconditions. So for example, given a true conclusion and a rule, it attempts to select some possible premises that, if true also, may support the conclusion, though not uniquely. And the example, a typical example, when it rains, the grass gets wet. The grass is wet, therefore it might have rained. You see this difference. So this kind of reasoning can be used to develop a new hypothesis, which in turn can be tested by additional reasoning or additional observational data. Yeah, and this brings us to a very famous image. So this is what is empirical inference, first stated by Gottfried Wilhelm Leibniz very early, so that you can understand visually what empirical inference is. So, you know, empirical inference is to draw conclusions from empirical data. And this is very interesting because the question of Leibniz already was what makes a function simple. And you know, this is very difficult to make it simple. And here you measure two observables and you approximate it in a straight line. So this is the green line. So you have x and y, for example, the two variables, and you have measurements here, and you approximate it by a green straight line. So you have a very simple equation, then y equals a times x. And as you easily understand, this can be very dangerous. Think of the famous story of Leibniz, who said that if you fling a fountain pen now, for example here, this can be from a fountain pen, you spill the ink on the paper, and then you interpret this, and you always will find the pattern. So the question is if this is really true. So this is really a problem of empirical inference. What does it mean for us in machine learning? Why are our problems hard inference problems? And I have mentioned this now several times. So this is just subsuming and concluding now. So again, please remember, high dimensionality, curse of dimensionality, many factors contribute. The complexity, our real world in the medical domain is non-linear, non-stationary, non-IID, non-identically independent, identically distributed. And you need always large top quality data sets, and you have little prior data, so you have no mechanistic models of the data. And this is a beautiful paper, and even if it is from 2006, I showed this to my students because this is a very valuable work which shows you that, for example, at the beginning you do just random guessing in AI. And then you need a lot of data, and then it becomes very powerful. So this is from the success examples in lecture 1 proven. Okay, so what makes it hard? So this is just for you as a homework. We skip the next 3 slides. This is just for you at Sunday morning. If you're awake at 3 o'clock in the morning and you are bored, then you can look up these slides and work on this. So we skip that for now and go straight on to interpretability. So let us return to our human AI interface problem. And here you have maybe an answer to future human AI interfaces, because they have to map the results gained from computer via these explainable methods. I have shown you one method. This was this layer-wise relevance propagation, and you have now to map the results from this method to our human understanding. And this is not so easy, because to learn causal structures from observational distributions, we need to understand how causal models and statistical models relate to each other. So for sure, what we need here is the ground truth, which we will see in a few minutes. So again, for you, this is very important to always remember: there's no correlation without causation, even if our statistical people in the early 19th said the difference, okay? So please remember, there's no correlation without causation. So, and also I should mention that you have seen in the first lecture that our best performing AI models are based on a stochastic or even on a model-free approach. So, and the challenge is really to infer causal relationships from this purely observational data. So we will shortly see this when we discuss the fundamentals of our Kandinsky patterns. So why is this important for deep learning? So Joshua Bengio emphasized during his Posner lecture at the NeurIPS 2019, this is one of the most famous conferences in the AI world, in Vancouver, the work of Amos Tversky and Daniel Kahneman is a good example of the current state of deep learning. So remember the bestseller from Daniel Kahneman from 2011, Thinking Fast and Slow. I would highly recommend to read this book. So Amos Tversky and Daniel Kahneman set up a central hypothesis about the dichotomy between the two modes of cognition. So here we have this original from 1974. So there's a system which they call System 1, which is here highlighted in blue in our slide. And this system is fast, instinctive, and unconscious. And Bengio considers this as current deep learning. This is what current deep learning can do. But then there is a System 2, which is called cognition, and which is considered as slow, logical, and conscious, and which is, according to Bengio, totally missing in current AI. So you see, really, this is the combination of human-computer. Human-computer interaction gets a completely new importance when seeing this like that. And maybe they call it now human-AI interactions or human-AI interfaces, but you see, this is a really pressing and open problem for future research. So the assumption is obvious now that we have to combine these both systems to solve certain problems. And on a side note, this work described in 1974, so Tversky died unfortunately in 1996, but Kahneman received the Nobel Prize for this work in 2002, and then in 2011 he published this bestseller book. So let us go back to our current state of the art. So how do humans generalize from a few examples? Sometimes, and Daniel Kahneman brings us back to the human in the loop principles. So, and you can remember when I showed you the first slides in lecture 1, about robustness. Yeah, why are people considered robust and are able to generalize from a very few examples? So sometimes, and I emphasize not always, here I highlight not always, humans are able to understand the context, to make inferences even from little noisy incomplete data sets, exactly what we have in the medical domain, and they can learn this relevant representation and to find these shared underlying explanatory factors. I repeat this because this is so important. So because they can draw the particular causal link, so of P of y given x with y mapped to x. And now you see that this mapping is so important. This mapping is extremely important, and this is the goal of future human AI interfaces. And to make it now a little bit more practical for you, question: how do human pathologists make diagnosis? So pathologists look at such histopathological images, and they follow the famous Schneiderman paradigm from 1990: overview first, then zoom and filter on demand. And they used medical terms which includes biological phenomena, for example, cells, tissue types, anatomical elements, abstract patterns. So they speak about, for example, a architecture, a penetration, a distribution, a grading. Here, for example, is a portal field, and so on. So basically, they form descriptions and they interpret it with their implicit knowledge. And now it makes clear why I have mentioned and elaborated on this explicit knowledge, implicit knowledge. So now it should be totally clear to you. And for example, if they say cells are smaller and closer together, it's a tumor. But it can also be an inflammation. It depends on the context. So it is important to note that generally in the medical domain, different modalities contribute to one single medical result. So, and one extremely important aspect here is the missing ground truth. And now we ask this: what is ground truth and where is the ground truth? So let us quickly rehearse ground truth, because this is so important, so just for a mutual understanding. So ground truth is defined as information provided by direct observation. Remember what we have discussed before, direct observation. So ground truth actually comes from mapping the surface of the Earth with airborne cartography. So down is the Earth, this is the ground truth, and the map is hopefully reflecting the ground truth in an abstract way. So it comes from aerial photography, okay? And so let us rehearse this, because it's so important. Ground truth is information provided by direct observation. This is the empirical evidence, in contrast to information provided by inference. Empirical evidence, again, as a rehearsal: information acquired by observation or by experimentation in order to verify the truth, so fit to reality, or to falsify, non-fit to reality. And this is in contrast to empirical inference. So this would be drawing conclusions from empirical data, observations, measurements, and so on. And now the most important is causal inference. This is now drawing conclusions about a causal connection based on the conditions of the occurrence of an effect. So all this inspired us for the design and development of our Kandinsky patterns exploration environment. So, and this brings us, or has motivated, what problems do we face in the real medical world? So what is our story? So the fact medical AI is currently extremely successful. Think on our success example in lecture 1. And some AI even reaches human level performance. However, in the real world, we are facing these challenges, for example, and we want to contribute this with ongoing work. So ground truth is not always well defined, especially when making a medical diagnosis. Although human scientific models are often based on understanding causal mechanisms, today's successful machine learning models or algorithms are typically based on correlation or related concepts of similarity and distance. And among others, this was the motivation for the development of our Kandinsky patterns exploration environment. And you surely want to know why this is called Kandinsky. So here, this is our one Kandinsky pattern. And I show you where this comes from. So this is the domain concept from histopathology. For example, what I've mentioned before. So true, the cells are smaller and closer together. It's a tumor. So this is a true pattern. This is generated from our Kandinsky patterns experimental environment. Yes, Kandinsky, I should mention that, was a famous painter, a Russian painter, Vasily Kandinsky, and he painted very abstract concepts, and he also wrote about it scientifically, and therefore we have named it in honor of this Vasily Kandinsky, our experimental environment. So we can, for example, generate such patterns. They are true, but at the same time we can generate patterns which are false. For example, here a completely random pattern, and counterfactual. For example, what if the cells are slightly bigger? And we have always the ground truth behind that, because these are mathematically exact objects. So this enables us to study causality in the sense of Judea Pearl, as we have learned before, the art of cause and effect. And we have extended this causality principle to causability. We introduced causability as the measurable extent to which an explanation received from such an explainable AI technique achieves a specified level of causal understanding. So this is an extension of causality, and causability, the name is not, so this is, let's say, intentionally chosen after usability, because this is really the measurable extent to which an explanation of a statement, for example, fits to a human user and achieves a specified level of causal understanding. And the measurement criteria include effectiveness, efficiency, and satisfaction in the specified context of use. And now it will become totally clear for you why I built this up so step by step, this context of use and this mapping and all these measurements and so on. So, and remember, mapping comes from this cartography, and this mapping is central for us and brings us now to the key point, how to understand and how shapes can be explained. So, and this is measuring the quality of explanation. So for these reasons, we have developed the systems causability scale. And this is a real recent outcome of our research to measure the quality of explanations with this effectiveness, efficiency, and satisfaction in the specified context of use. And we have chosen the term causability in reference to the word usability. So please remember always, it is important to note that in medicine many different data contribute to a single result. So therefore we need a multimodal view. Why is this important? That brings us to the conclusion, and I know your coffee is already boiling and you are now curious for the last slide. So the very last slide. So in medicine, we need something what we call multimodal causability. That means human AI interfaces which enable a domain expert to ask questions to the results in order to understand why a machine came up with the result. And to ask these what-if questions, these so-called counterfactuals, to gain insight, deep insight and understanding into the underlying explanatory factors. For example, how will the result be affected when leaving specific features away? So with these words, I say thank you, and please enjoy now your coffee. You have deserved it.